Great. So let's talk about problem. So what was the thing that we discussed previous session? So we discussed about 3 approaches to solve problems. And these 3 approaches, we talk about something like divide and conquer, but divide and conquer was actually part of greedy algorithms. So we had 3 approaches: backtracking or branch and bound, that we talk about them, then greedy algorithms and dynamic programming. And we mentioned the relation between these problems, essentially, that backtracking, possibly they can do the role of greedy algorithms if you do it smartly, such that or do it also in the branch and bound way, that if the greedy works, then they can work. You can actually design such kind of things. If not working, then try other possibilities. Greedy algorithm would be very good if they can work and they give the solutions. Sometimes they are not giving the optimum solution, but they can give approximate solution. We talk about them. And finally, we talk about the memoized technique for dynamic backtracking algorithm to make them essentially dynamic programming with very little change in the code and make the running time much faster. Such as those subproblems that we need to solve over and over. If we just solve it once, we will keep the solution in an array, and next time that we are coming, we are just using that. And by the way, this is a very important approach in almost, if you go nowadays, if you talk about, for example, big systems like, I don't know, Amazon, Google, or others, all of these are doing this kind of pre-processing because these are online services. These online services, they have a very little time essentially to show you, generally like 20 milliseconds or 100 milliseconds. That's the range that they need to show. That's the time that they have it to bring the page for you. And there's a limited time. So to make sure that there is no delay, it is called render rate essentially, or rendering time. There, they need to pre-compute everything. So that's the same thing that we are doing. That so always this pre-processing, as much as you can, will be very helpful to get fast algorithms. And that's the thing that we have seen talk about the dynamic programming. I just want to we gave some examples. I want to give one more example of dynamic programming on graphs, because we talk about the graphs. And then I will talk also one example of these greedy algorithms. And then we will go to the next step. So what do we want to talk here first? Let me okay, so I need to do it with this one. It would be a bit harder to write, but anyhow, so let's do this one. So what is the independent set problem? So the independent set is an important problem that here you are given a graph. You want to find a set of vertices such that no 2 vertices in the set are no 2 vertices that they have an edge will be selected. So what's the meaning of that? So you have, say, you have this graph G, and here you want to make sure that if there are 2 vertices like here and here, then, and you select this guy and you select this guy, then there should be no edges between these 2 guys. So there should be no edges between these 2 guys. This is the one that is called an independent set. And what is the idea here? We want to find the largest independent set in a graph. So if you consider the complement of the graph complement, we talk about independent set and clique. The clique is the one that if you take the graph and make the complement, every edge that is there, you just don't put it, or every edge that is there is not there, put it. If you do the complement, then independent set and clique problem would be the same. Clique would be that you want to select a set of vertices such that all vertices are adjacent. Now, let's consider this problem that you are given a 3T and you want to find the largest independent set in it. So here, without loss of generality, assume that the tree is rooted at the vertex R. So whenever you have a tree, we discuss a lot about the trees, how you can represent trees. And I mean, we don't talk about the data structure, but say you have represented it, a tree, and there is one vertex R, and we want to solve the independent set problem on trees. Good. So lots of problems on general graphs. This independent set problem actually is a very hard problem in general graphs. In some sense, like the best algorithm that currently we have it for that is just report one vertex in the hard instances. But on trees, these problems can be solved in polynomial time and fast algorithms. Here we want to talk about that. And generally on trees, one approach that works well is dynamic programming. That when you want to solve a problem for tree, first you are solving for subtrees. Like vertex, I mean, has some children. Each of these children have some kind of trees hanging there. You will solve for these problems, and then you will combine the solution to get one level up. And then when you come all the way up, then you have the solution that you want. So that's the general idea. And we are doing the same thing here. What is the problem? So you are given a tree T. You want to find a largest independent set in it. And assuming that, I mean, this tree has a root R, first, the way that we are doing it, we are thinking about essentially the backtracking approach, or a recursive algorithm that can solve the problem. So this is IS means independent set. I will just define it. So this is somehow this is the case that this is the base of induction. If a tree is only a leaf, then the size of the independent set would be 1, because you just select that. Now, so this is mainly this recursion. When you write this recursion, then you can write a backtracking algorithm, or you can do Memoized technique to make it dynamic program. Later, if you want, you can do it in a non-recursive way with a little bit better in terms of overhead. But I mean, these are the recursive algorithms are very nice and like less errors there. Yeah, what's the question?
So can we move the largest independent set always be the set of leaves?
Not necessarily. Yes, of course, that's one option. So this is a good question. So, okay, if you want to find the independent set in a tree, is it the case that always the leaves are the case? It is not. So leaves can be included there, but I'm just giving one example here, for example. You see here, this is the tree. And here in this tree, as you can see, yes, you can select the leaves, but also you can select what? The root as well. Yes, so the leaves are generally good. And you can say actually it should include leaves always, but you can have some other vertices as well. So that's the thing that you want to find. So this is the whole idea is this formula. This is the one that you need to understand. Good. So what does this formula say? It's consider essentially so consider this guy, which is I. So let's call this guy I. And say J is the child of this guy. J, and say J also has some children. Good. He said that either it's a leaf, which is the size of that would be 1. What about if, and generally this is the approach that is important for trees. Again, we are just always considering a rooted tree, and we are writing essentially recursion. Generally, we are doing, the proof would be also induction on the height of the tree that we are considering, height of the subtrees, and then we write a recursive algorithm to come up. So that's a good example that shows actually how can we solve a problem on trees. And generally, if you can make the graph trees or approximately trees, this is some concept of approximation. It's called bounded tree widths. But the trees means that these are the graphs which are similar to trees. They are not trees, but they are similar to trees. And then for those problems, actually, also we can have a good dynamic programming. And all of this dynamic programming using the same approach that we are doing. It's more involved, but the main intuition is this one. So you consider a vertex I. So always you are going from essentially bottom up. So consider I. So there are two cases. Either this I guy is in the independent set itself. So if this guy is in the independent set, then what will happen?
You cannot pick its children.
Then we cannot pick its children. So then we will go recursively find the best independent set here in the grandchildren, essentially. Good. So consider the grandchildren. For each of them finds the best solution, because if we cannot find the children, but all of the grandchildren, if there's an independent set, we can select them. So that's the thing that we mentioned. So we will say that yes, either you go K is a child of I, then find the independent set for each of them, take the union plus 1, Y plus 1 because of I. Or the other option is that you don't select I. So in that case, then you can select the best thing for the children. So for each of these children, find the best solution and take the union. Good. That's the one actually that gives you the solution for the problem. And now you can actually, then if you want to do that, I mean, of course, you don't want to recompute this one. So for any vertex, when you are computing IS of I, you will just have an array of size n, and you will just save that independent set size there. How can we find the actual independent set? Again, the same way that we have mentioned. We are essentially bookkeeping about which of these solutions was the correct things. This one or this one. So depending on that, whether this formula or this formula, the maximum comes from any of them, we will just do the bookkeeping or take the log of this in some array sol, and then we are writing another recursion algorithm that comes there and decides which one was the correct thing and reports. It's exactly the same technique that we talked previously. So that's a general way. I want to say that this is the important thing. So we talk about two important problems here. One is the one that I have mentioned for longest common subsequence. That's very important for editdistance, which is one of the basics of essentially computer science, and all of this text stuff databases are using essentially somehow. This is a very fundamental problem for them. And also the other one, independence, is an important problem, but more importantly on trees. That gives you an idea how you can solve the problems on trees. That this is the way that you can solve bottom up, and you can write the recursion algorithm, then you will make it memoized, and that you have a very good algorithm. Yes?
So for the case when I isn't selected, for the independent set, I won't it just completely different?
Sorry, what was that?
When I isn't selected,
yes,
then won't the independent set J always be just there?
It depends. It might be the case that in that case, I mean, note that J has also a subtree in it, correct? A tree, it is hanging from J. So it might be the case that you don't select J as well, and then you are selecting all of his children. That's like you should, I mean, as I mentioned, for example, you can say that the leaves will be in the tree, but always would be on that independent set. But these are some of the things that you need to prove. Yes, I mean, you can think about it, what will happen in that case, but in general, that's the, I mean, general algorithm that you have for it. Good. And I think this is also important. When you do that, you can say that the running time of this algorithm actually would be order n, the size of the trees. Because again, you don't compute each guy more than once, essentially. And to compute each guy, you are just going to two other arrays that you have pre-computed. Because this is the two arrays that you are going and you have pre-computed. So that would be the running time of that. Actually, this would be the number of order of edges, but the number of edges in a tree and the number of vertices are the same order. Good. So these are the two important things. Now I wanted to give one other things here. Oh. It started working. I don't know why it didn't work before, but now it's working. Good. Now I have more power. Good. So next problem that we want to talk about is the binpacking problem. This is the one that I want to talk about, approximation algorithm. So approximation algorithms are very important set of algorithms. So far, we have everything that we have. So this is like algorithms that we are talking about. So algorithms is like a very wide area. Like nowadays, when they say an algorithm, that generally means all the machine learning, etc. These are also parts of the algorithms. So it's a very wide area. We talk about, I mean, general classic algorithms in this class, Introduction to Algorithms. However, we talk about randomized algorithms as well. Like, for example, when we talk about hashing or quicksort. And we discuss how you can actually analyze. Here, there is another, so that's a very big area of algorithm, randomized algorithms, and why they work. Another area is the approximation algorithm and why they work, essentially. So, approximation algorithms are the set of problems that generally you want to get a very fast algorithm, or sometimes for this problem, which are, we will call them essentially NP hard, that we cannot solve. So far, we don't believe there's a polynomial-time algorithm. So, okay, we cannot find the exact things, but find maybe an approximate solution. Generally, we want to get some approximation factor which is close to 1. 1 means exact. Approximation factor more than 1, it means that like it is twice the optimum, for example. Or sometimes also we mean half of the optimum. Both of them we call it two approximation. Let's see an example here, and you get, again, this is the introduction to that. You can take lots of classes, or you read materials, or see videos on that one, but you get some ideas how we prove actually such kind of approximation. So what is the problem? It's a very binpacking problem, is very famous problem. So you want to packing different size object into a fixed size bins, using as few bins as possible. This is like one of the most practical problems that you have worked on it. So you want to put this one essentially put in the boxes. You want to move from this place to other. You want to just make sure that you are not, I mean, this is minimum number of boxes, because generally they take a space and you want to minimize the number of boxes. So let's make it, I mean, a bit more formal problem. So you have x1, x2 to xn. We set up real numbers. So all of them are between 0 and 1. You want to partition these numbers into as few as possible subsets, such that sum of the numbers in each subset is at most 1. Good. You want to put them in the bins, essentially, this number. And again, this is actually, this is the one-dimensional version. You can define two-dimensional and others, three-dimensional, etc. And there are some algorithms for that. But here, again, the basic algorithm, I want to give you the ideas. So these are the numbers. You can just think about these numbers, I don't know, 0.1, 0.9, 0.2, 0.8, and 0. I don't know. 1. For example, in this case, you can put these two guys in one bin, these two guys in one bin, and this guy in another bin. And each bin has a size 1. All of these guys are between 0 and 1. The bins have size 1. You want to find the minimum number of bins. Good. Now, what is a greedy algorithm? A natural algorithm is this one. Which, I mean, generally, when you want to do greedy algorithm, I would say if you sort them, it would be, that may work better, essentially. So here you can put this one, put x1 in the first bin, and then for each I, put xi in the first bin that has room for it. Good. So it's a very natural algorithm. You will just consider this one, the first guy, we put it the first guy, then the next guy. If you can put it in this one, you will put it. If not, open a new bin and put it there. Anytime that you can put it, if you can put in one of these bins, put it there, otherwise open a new bin. This algorithm is called first fit. I mean, you can think about that. You may want to actually sort the guys before, like for example, from highest, largest to least, and then you do this one after that. That's one way. It's not clear that sorting always helps, because in some sense you want a combination of big one and the small guys, because you don't want to just put like new bins every time. But anyhow, so you can consider this one. You can have a different algorithm. This problem, actually, you cannot find the exact bin packing algorithm. Like finding the minimum is an NP hard problem. That we will talk again. We don't believe that this problem can be solved in polynomial time, at least so far. An approximation algorithm generally works for this type of problem. Now, however, I want to say that this algorithm maybe does not find the best solution, but it's not that bad algorithm. So this algorithm, as I mentioned, this greedy algorithm is called first fit, the first one that you can fit it. Now, I want to say that the first fit algorithm uses at most twice plus one the best possible number of bits. Good. So then, like if there is some algorithm, like you can think about, I don't know, God or anyone, or prophet or anyone, that gives you the best solution for you, you can guarantee that any number that you put, or that person or that creature is doing that, you can put it 2 times plus 1. Generally, that's, I mean, the concept of God or prophet or anything, just call it as an opt. Opt is the one that has the force, I mean, the whole power and can find it. We may not be able to see what does it do, but generally in the approximation algorithm, we try to massage the opt. So from opt, we don't know what is exactly that, but we try to get some ideas about it. And then we try to find a solution which is comparable to the opt. That's the whole idea of approximation. So you always need to start, you need to have some opt and you need to use some properties of opt. Otherwise, you cannot compare with the optimum solution. Good. So let's see the example here, the theorem that I want to prove, that the first fit algorithm uses at most 2y plus 1. Good. So this is the main observation. The first fit algorithm cannot leave 2 bins less than half full. Good. If 2 bins are less than half full or less than or equal to half full, it means that one of these bins that whenever you want to put it there, you could put it in the first guy. One of them you opened first. Why is this guy there? These guys, all of them can go to here, essentially. So like if you have two bins here, that both of them are less than half full, like half, less than half here, then this guy says the first you open. Then anything that you have it here, you could put it here, essentially. So it means that it should be nothing less than half. Now, so what do we have? Then we have that. So we know that the number of bins that we have used cannot be more than twice the sum of the size of all objects. Because, I mean, anytime which would be like the total thing, I mean, the number of bins, each of them is half full. So if you sum it up over everything, at least, and each of them is like twice that number we can use. Let's see actually a better formula for that. So that's the thing that we want to do it. So this is the formula that we can get this. So consider the optimum algorithm. So that was the intuition that I have mentioned. Now I want to give you the formula. Consider the optimum solution. We know that optimum is greater than or equal to the sum of the xi's, correct? Because sum of the xi's that you will do it, at most each of them take 1. The best thing is that the opt should be greater than sum of these x's. Clear? Now, because of the observation that I have mentioned, we know that this is like this is the floor of number of bins over 2. It should be less than or equal to sum of these guys. Why? Because we cannot have any 2 half bins essentially. So if you just consider the number of bins, and then I will take the floor of them. So if they are even, if they are odd, I will take the floor like of these bins. That should be less than or equal to sum of xi's. Exactly because of this observation that I have mentioned. Now, then after that, it is easy. We know that the number of bins over 2, it is always greater than, floor of that is greater than number of bins minus 1 over 2. Good. So I have this formula. Number of bins minus 1 over 2 is less than opt. So you just get the result. You will get bin, number of bins would be less than 2 times optimum plus 1. So the main observation was this part essentially. That's, most of them actually, these are all interesting. This one was interesting, and this one was interesting. So this algorithm actually gets a solution which is twice the number of opt plus 1 maybe. Good. There are algorithms that are working better. You can get actually, if there's an optimum, you can say that for any constant epsilon, you can get some algorithm which is 1 plus epsilon times optimum. But then the running time of this algorithm will depend on 1 over epsilon. And in general, it should be exponentially 1 over epsilon. Because as I mentioned, there is no exact algorithm for this problem. But instead of 2 approximation, you can get 1 plus epsilon approximation. Like very close for any epsilon greater than 0. But the running time of this algorithm would be a function of 1 over epsilon. Good. And it cannot be, I mean, you cannot get essentially epsilon 0, because then in that case, you can solve the problem. I mean, you can possibly solve the problem, but then P is equal to NP and lots of, the whole word changes probably. Good. So that was the example of approximation algorithms and the way, so, and that was important. We will consider opt. We will, instead of opt, we try to relax it in some sense. We relaxed opt to some other things. It should be at least some of the items. Then that one, we could compare it with the number of bins that our algorithm is doing that, and we could get the approximation algorithm. Always this happens. Optimum, you will change a little bit the optimum, because you don't know what is optimum, but you need to get some upper or lower bound on optimum. Then that would be something that you can compare with the performance of your algorithm, and then your algorithm compared with this relaxed version, and then this relaxed version compared with the optimum, so you get some relation between your algorithm and optimum, even though you don't know what is optimum. This is a good example. You can see lots of other examples, essentially, in other places as well. Just, it's a big field approximation. Good. Let me just draw this one. Now, good. So this was essentially just talking about the different ways of algorithms and the approximation algorithms and the ideas there. Now,